Operational technology runs the physical world. When an industrial control system is compromised, the result is immediate, violent hardware failure. This network diagram illustrates a fatal architectural flaw, the flat network. Here, enterprise IT systems like laptops and cloud servers are connected directly to industrial machinery, the SCADA servers, human-machine interfaces, and programmable logic controllers. Standard enterprise security relies on rapid, constant patching and system reboots to stay ahead of threats. However, on a factory floor, physical uptime is the absolute priority. You cannot reboot a turbine while it is spinning at 3,000 RPM. Applying standard IT security assumptions to unpatchable industrial infrastructure creates a direct path for digital intrusions to cause catastrophic physical damage. To prevent those failures, industrial environments rely on a specific blueprint, NIST 800-82 Revision 3, the definitive standard for operational technology security. Because industrial endpoints often cannot take software updates, this framework mandates a 5-layer defense-in-depth strategy. It builds protective barriers around the vulnerable machinery rather than trying to alter the machinery itself. Auditors implement these defenses using a 7-step risk management framework. This systematic methodology takes an environment from total vulnerability to a verified, monitored state. We are going to conceptually rebuild a vulnerable factory floor by running it through this exact risk management framework process. Industrial auditing engineers a structurally resilient architecture designed to survive an active attack, shifting the objective from simple compliance to physical hardening. The framework begins with the prepare phase. This requires establishing a strict OT security policy that is entirely separate from corporate IT and appointing a dedicated OT security officer with the authority to enforce it. Once governance is set, we must execute a total physical asset discovery. Every programmable logic controller, remote terminal unit, and human-machine interface must be accounted for. Auditors log the exact firmware version and cross-reference it against known common vulnerabilities and exposures, or CVEs. Next, we map the exact communication pathways to know precisely which machine is talking to which controller. These pathways carry specialized, plain-text industrial protocols. Identifying protocols like Modbus and DNP3 is critical because they were designed for reliability, not security. With the map complete, we move to the categorized phase. Here, we rank these mapped systems as low, moderate, or high impact, evaluating the exact physical consequences of failure across human safety, operations, and regulatory compliance. Defending an industrial environment is impossible until every single physical asset and its baseline communication behavior is completely quantified. Now we enter the select and implement phases. We establish a hard physical and logical boundary, represented by this firewall, separating enterprise IT from sensitive OT assets. This segmentation strictly isolates operations. Unauthorized corporate data traffic can no longer reach the factory floor. This firewall is just one component of the overarching 5-layer defense-in-depth architecture required by the checklist. Layers 1 and 2 focus on the human element, implementing rigorous management policies and strict physical security controls, dictating who can even enter the facility. Layer 3 introduces network controls. This relies heavily on the IT and OT firewall boundary we just established to filter traffic. Finally, layers 4 and 5 apply hardware and software controls directly within the isolated OT zone, locking down endpoints as much as technically possible. Even within this secure architecture, administrators must continuously audit internal data flows, aggressively restricting traffic so that only essential operational commands can pass between devices. And because hardware can fail even without a cyber attack, the checklist mandates automated backups for critical configurations and active periodic testing of physical failover mechanisms. Proper network segmentation acts as a structural quarantine, ensuring a routine business email compromise cannot cascade down and manipulate physical machinery. Digital security is completely bypassed if an attacker can simply walk up to a terminal. Physical access controls to the hardware are mandatory, requiring ID badges, visitor logs, and overhead CCTV to monitor sensitive areas. Inside the systems, operators must use unique passwords, not shared accounts. If a command executes, there must be a definitive record of who issued it. Furthermore, any remote access by external vendors into the OT environment requires multi-factor authentication. A compromised vendor password cannot grant access to the factory floor. As we lock down the environment, we invariably encounter the legacy problem. We've highlighted one older programmable logic controller in bright red. These legacy systems run outdated operating systems that reject modern firmware updates, incapable of receiving patches without hardware failure. The engineering solution is compensatory controls. We neutralize the risk by restricting all network access to the unpatchable asset, isolating it from the factory floor. In industrial environments, acknowledging a structural vulnerability and engineering an isolation box around it is often the only viable alternative to unfeasible patching. When updates are actually possible, there is a cardinal rule of OT maintenance: never test patches or firmware updates directly on live production systems. Every single update must be verified within a dedicated, isolated test environment before it ever touches the production floor. To verify our newly secured architecture, we enter the assess phase. This requires a formal audit using tools like the Cybersecurity Evaluation Tool, or CSET, specifically version 12.2 and above, which scans the completed network. CSET directly maps the network's current defenses against the specific controls listed in Appendix F of the NIST 882 Revision 3 guidelines. The tool rigorously verifies that any compensatory controls we built around legacy systems are mathematically sufficient for the system's impact category. This brings us to the authorize phase. Executive leadership reviews the audit report and officially accepts the residual risk, approving the system for operation. A security audit only holds weight if it measures the environment against a standardized, reproducible control framework like NIST. Post-authorization, the monitor phase begins. The strategy shifts from static auditing to the continuous monitoring of real-time logs, ensuring secure, uninterrupted industrial operation. Facilities must maintain an incident response plan specifically tailored to operational technology. An OT breach behaves very differently than an IT breach, and responders must prioritize physical safety above all else. Teams must continuously update their business continuity and disaster recovery plans, adapting them to new threat intelligence and evolving operational realities. By rule, this entire checklist must be re-executed annually or immediately following any major architectural change to the factory floor. This endless cycle embodies the core cybersecurity framework loop: identify, protect, detect, respond, and recover. Securing operational technology is not a destination. It is a continuous engineering discipline required to protect human safety in an increasingly hostile digital landscape.